All right, we're back. This is page 3, notes 14, talking about the logistic differential equation. And we're going to actually do a problem here, so that's kind of nice. So we want to solve y prime equals 0.3y, quantity 4 minus y. That is not how I want it to look. With y of 0 equals 1, find the value of y when y prime has a max. All right, there's like a million questions. But first, do we first have to solve this? Find the value of x when dy dx is at a maximum. What special point on the graph is this? That's a point of inflection. Find the limit as x approaches infinity. Sketch the solution curve. Okay. So first, let's solve this thing. So we solve by memorization, basically. So we're given dy dx is 0.3y, 4 minus y. So what I'm going to do, I need this to be a 1. If it's not a 1, then the way I have it memorized is not applicable. So I'm going to factor a 4 out and get 1.2y, 1 minus y over 4. So when you factor out, it's like dividing. That's why it became y over 4. And now, this is good, right? That's a check mark right there. Different color check mark. That's a check mark. So from this, I now know that k is 1.2, and I know that L is 4, simply by identification, right? It's k times y, 1 minus y over L. So we just look and we see. We also know that the initial condition is that y of 0 is 1. So since y of 0 equals 1, we can solve for a. So a is L, which is 4 minus y0 over y0, so 3. A is 3 a lot in the problems that I write. And I don't know if there's like a reason for that or whatever. I mean, I guess it's coincidence. But so our solution is L over 1 plus A, which is 3e to the negative k t. And there you go. Oh, well, x is what I should use because it's dy dx. So x. There we go. So this is our solution. So let's highlight that. Now, what are these other questions? Find the value of y when y prime has a maximum. All right, so y prime has maximum. We know this. It's when y equals L over 2. Therefore, y equals 4 over 2, which is 2. That's always going to be the case. So you have a point of inflection on the curve at y over 2. When the population is y over 2, at half of the limit, you get a point of inflection. That's also the maximum of the derivative. The derivative has a maximum when y is equal to L over 2. Remember, the derivative is a function of y. It's not a function of x in this case. Very weird. It's like an implicitly defined derivative, I guess. And then what special point? That's going to be, find the value of x when dy dx is at a maximum. So we have to solve that. So this has a general solution. I don't think it's worth knowing, even though, like, I mean, I'm probably wrong. And so what's going to happen is we get 1 plus 3e to the negative 1.2t equals, so 2, right? So basically cross multiply, like bring this over and bring that under, whatever, you know, algebra 1. Subtract 1, divide by 3, e to the negative 1.2t. These should all be, all my t's should be x's. When I'm doing differential, when I'm doing the logistic, I always use t because I feel like time should be the thing. So I'm subtracting 1, dividing by 3, I get 1/3. And then I'm going to take the natural log of both sides. And I get negative 1.2x is the natural log of 1/3. Divide by negative 1.2. So here's the thing. I get negative natural log of 1/3 over 1.2. But that negative can be the exponent of the 1/3. So it's 1/3 to the negative 1, which is actually just the natural log of 3 over 1.2. So, I mean, if you follow the bouncing ball for like where things came from, this looks like it's the natural log of a over k. But I don't have that memorized. And I don't actually, I mean, it looks like that. I don't actually, without doing it, which wouldn't take very long, and I'm not going to, without doing it, I'm not sure that that's true, but I'm pretty sure that's true. So this happens when x equals the natural log of 3 over 1.2. And then we're also supposed to, oh my God, find the limit. Where are you supposed to do all of this? The limit as x approaches infinity of y is equal to 4. I mean, we've known that since like the first line of the problem. Point of inflection, good grief. Y has POI at natural log of 3 over 1.2 comma 2. And then sketch the curve. All right, so let's see. I think this is like 1, 2, 3, 4. So great dotted line there. The initial condition is 1. And so we know the point of inflection is going to happen like, so what's the natural log of 3 divided by 1.2? I don't know. But I bet it's like somewhere around like here maybe. But like, what are those tick marks? I don't know. So you want to be concave up as much as you can, and then switch the concave down there. I think that's a good solution. I don't know. Are there fewer questions here? 10,000 acre forest, 10,000 actually immaterial to this problem. Capacity of 1,000 deer. So carrying capacity, that's telling us that L is equal to, that's telling us L. So carrying capacity of 1,000 deer. So that's L is 1,000. So you got to be like good at reading these problems. Assume the population grows logistically with growth constant. K has weird units. So it's like 0.4 per year, because you're going to then multiply. Like, look at the thing. Like, if this is in years, then the units need to cancel, which means that this must be in per years, so that you can do years over years and have those cancel out. So the units are pretty weird for those sorts of constants. It's growing by like 0.4 per year. That's it. So K equals 0.4. I don't spend a lot of time thinking about those units, but every time I do, I'm like, that's weird. Initial population of 100. So we're just given everything we need. How long does it take? Okay, well, that's a different question, but let's solve this thing. So P of T is going to be L, which is 1,000 over 1 plus, oh, we got to find A. A is going to be L, 1,000 minus the initial over the initial, which is just 9. So 9e to the negative k, and then t. So how long does it take for the deer population to reach 500? 500 equals 100, nope, 1,000 plus 9e to the negative 0.4 t. Okay, so we do our thing, we get 1 plus 9e to the negative 0.4 t equals 2. Subtract 1, divide by 9, e to the negative 0.4 t equals 1/9. Then we divide, we get, no we don't, we natural log, we get negative 0.4 t equals the natural log of 1/9. So we're getting like, I think we're getting the result we expected. We're getting the natural log of A divided by K, but I also think not worth memorizing. So natural log of 1/9 divided by negative 0.4, which is the same as the natural log of 9 for the previously discussed reasons over this. So that is the time. So we could write a sentence about that, but all right. The population reaches 500 when t equals the natural log of 9 over 0.4. So that's the point of inflection, because it's half of the limit. So let's see if we can do this. I'm going to assume these are by 100s. Also, they're kind of hard to see. 4, 5, 6, 7, 8, 9. Okay, so our limit like that. And then our initial population is 100. And if I knew what the natural log of, 9 divided by 0.4 was, I might know what these tick marks are along the horizontal rather, but I don't. So I'm just going to draw, and then we'll know when we get there. So let's say, oh boy. That looks okay to me. So this I think is going to be the natural log at 9 over 0.4 comma 500. That's our point of inflection right there. All right, I think that looks good. And I think that's the end of this page. So I'm going to stop there and I will come back in the next video and do some more. So I will see you then.